a splendid morning to one and all connected here. Every new day brings new hope, new thoughts, and thinking. Now I am considered in becoming Council of Scientific and Research today's on challenges and opportunities for Department of EEE, IFETCE College of Engineering. That idea can change one step and start a journey. But your prayer can change even the impossible. Let us pray Almighty God. Many of you have made a huge effort to join us today. On behalf of the IFETCE College of Engineering, we are deeply appreciative and offer you our most grateful welcome. Now I call upon Professor T. Ram Pratish, Head of EEE Department, to deliver the welcome address.
Good morning, everyone. Welcome to the blossoms on the bottom of the Rashtriya House. On behalf of the Department of Electronics Engineering and IFETCE College of Engineering, I take extraordinary pleasure in welcoming all of you to the CSIR sponsored today's educational seminar on key challenges and opportunities for recycling and batteries. I also want to thank cards and bid a very warm welcome to Chief Guest today, Dr. Naveen Kumar, Senior Scientist, CSIR. Thank you, sir, for such a contribution and joining us today. I welcome our pipeline principal, Dr. P. to sponsor support and engagement with such a design program. I heartily welcome our dynamic lead director of the research force in all our activities. I cordially welcome the R&D of the heads of various departments and functional units. I'm very much delighted in welcoming all the professors and their faculty friends from various departments of our institution. I welcome the program conveners, Professor Jeshwar and Professor P. Virla, Department of EEE, who steered us in organizing this seminar. It's my pleasure to extend a cheerful welcome to all the participants who are gathered here across the country to participate in this extraordinary event. I place my sincere appreciations to the faculty who have organized to guide us together through this event. Last but not least, I would like to take this moment to remember Dr. P. Manivandan and Dr. Sujit during this wonderful event. Welcome, honored.
Thank you, sir. We all need someone who takes us to the next level. Now I request our Vice Principal and Dean Academics, Dr. S. Matilda, to present the inaugural address.
So, respected chief guest of the event, Dr. Naveen Kumar Chandrasekhar, Senior Scientist, CSIR, Head of the Department, Professor Ram Pradesh, Convener, Dr. Jay Shiva, Co-Convener, Professor Vimala, and my dear participant friends. A very good morning to all. So at this juncture, I congratulate the convener, Dr. Jaishiva, and co-convener Vimala for coming up with such an innovative and thoughtful topic, key challenges and opportunities for recycling electric vehicle batteries. So as all of you would know, the entire world is moving towards electric vehicles, and so the disposal of the batteries is going to be a big challenge, along with the opportunity that electric vehicles are presenting in the form of entrepreneurship, like recharging stations and other things, and emission free vehicles and other things. The one main drawback which we are going to face over the years is how to dispose these batteries. So most of you would have come across lead acid batteries. Now these lead acid batteries, the recycling of these lead acid batteries is comparatively simple, and most of you would have come across one way of disposing it. The common, the common trend which we see, uh, how these lead acid batteries bodies are reused at homes is you grow a plant. Okay, most of you would have seen that. Okay, so this is one simple way in which this battery is reused. That to reuse is done after so many usage, so many recoveries and other things. But it's not the same with these lithium ion batteries which are used in the electric vehicles. So as statistics says that around 2040, 50 million electric vehicles are going to be on the roads, and the average life of each battery is going to be 10 years. So by 2040, we are going to have 10,000 tons of electric batteries, or these lithium ion batteries, which are going to be disposed as scrap. Now, the problem is dealing with these lithium ion batteries is the recycling or the disposal is going to be very difficult, as it is hazardous, fire hazard, as it is going to create a fire hazard. Like, you just cannot dispose this battery because it'll ignite easily. So now the challenge is so many companies have started coming up now itself as to how to find out the ways and means to dispose these batteries. So, a seminar of this type is at this right juncture is just to create a thought, or to create a spark in all the young minds who are attending this seminar as to how to dispose these batteries, to find out way and means. This also could become a startup or a entrepreneurial venture of some of the participants in this, so that by the time the disposal becomes a hazard or it mounts up, we would have come out with a method for disposing this. So uh, as per my conviction, or as per my thought, I feel that this seminar is going to benefit most of the participants who are here, who are attending this, so that you can think of some innovative ways, or if you are a faculty, you can take it back to your students and propose a method wherein you can dispose this, and you can start up your own venture. So I congratulate convener Jay Shiva and the co-convener Vimala once again. And I also take this opportunity to thank CSIR for having supported us in and sponsored this event, so that we at IFET feel proud that we have been recognized, and we are indebted to CSIR for so many other reasons also. Thank you so much, sir. And thank you so much, participants, for taking your time off and joining this seminar. Thank you, one and all.
Thank you, ma'am, for your inspirational words. Now I invite Dr. S. Jay Shiva, Associate Professor, Event Convener from EEE Department, to deliver an opening report.
A warm greetings to one and all. I feel very much honored in presenting the opening report of CSIR sponsored 2 days national level seminar on the topic of key challenges and opportunities for recycling electric vehicle batteries. In this occasion, we feel proud to share that 234 external participants have been registered from various institutions across the nation have shown their interest in attending this seminar, out of which 100 participants has been shortlisted on first come first serve basis. This national seminar throws an insight on current trends that brings a clear vision on smart world into reality in electric vehicles. The objective of this program is to support the society and research people by exploring the various concepts of energy storage technologies, battery management in electric vehicle, and the impact of renewable energy for electric vehicle applications. This 2 days seminar program has been scheduled with 4 sessions with the prominent speakers of various delighted organizations. The first session will be about the refurbishing and recycling of lithium-ion batteries, and it will be handled by our renowned chief guest, Dr. Navin Kumar Chandrasekhar, Senior Scientist from Central Electrochemical Research Institute, CSIR Karaikudi. And the second session of day one will be delivered on the topic of converter selection for electric vehicle battery charging by Dr. P. Parthiban, Associate Professor in the Department of Electrical and Electronics Engineering from National Institute of Technology, Surathkal. On day two, the third session will be about the life of electric vehicle batteries and designing of charging station, and it will be delivered by the chief guest Dr. S. Senthil Kumar, Associate Professor in the Department of Electrical and Electronics Engineering from National Institute of Technology, Trichy. And the last session will be about the role of renewable energy sources in electric vehicle batteries and its application. And the session will be delivered by Dr. Hadi Nabipur Afrozi, Faculty of Engineering, Computing and Science from Swinburne University of Technology, Sarawak Campus, Malaysia. Finally, I would like to conclude that the above framed session from the of CSIR sponsored seminar will be an eye-opening to everyone, and I hope that you will be surely make use of this wonderful opportunity. A great journey is waiting on the topic of recycling electric vehicle batteries for you all. Thank you.
Thank you, sir. It's about time we start using multimedia to convey our department achievements. Let us have small glimpse of EEE department activities.
IFET College of Engineering has emerged as an autonomous institution of repute and was established in the year 1998 under the aegis of Indo-French Educational Trust. The college was located in East Pondy Road, Gengarapalayam, Viluppuram. For the past 2 decades, IFET College of Engineering is offering high-quality education to the society. The undergraduate programs offered are Artificial Intelligence and Data Science, Artificial Intelligence and Machine Learning, Computer Science Engineering, Electronics and Communication Engineering, Electrical and Electronics Engineering, Information Technology, Mechanical Engineering, and Civil Engineering. The postgraduate programs offered are ME Applied Electronics, ME Computer Science and Engineering, and Master of Business Administration. IFET College of Engineering has a remarkable infrastructure like renowned laboratories, digitized classrooms, central library with large volume of books and reputed international journals, good hostel facilities, well-defined educational system, and experienced faculty to mold young graduates to serve the community. The college has gained high reputation in the society through its academic excellence, continuous placement records, and active research and development works. The administrators of our institution are Mr. K.V. Raja, Chairman, Mr. K. Shivaram Alva, Secretary, Mr. R. Vimal, Treasurer, Dr. G. Mahendran, Principal, Dr. S. Matilda, our Dean Academics and Vice Principal. The institution approval and affiliations are Directorate of Technical Education, Government of Tamil Nadu, AICTE New Delhi, permanent affiliation to Anna University, accredited by NBA and NAC, recognized by UGC, achieved platinum status in AICTE CII survey, recognized research center by Anna University. The institute vision statement is to deliver quality education of international standard and produce engineers competent at regional, national and global levels. And the mission statement is striving to be the best in what we do, persistent and relentless in our pursuit of quality and never being satisfied with the status quo. Our institute received Center of Excellence for Cisco, Solver Minds, Aspire Systems, Wipro Vision 10X, Infosys Campus Connect. The department vision is fostering the students with technical competence in electrical and electronics engineering to take up challenging roles in the global context. The mission is to impart high quality education with a plethora of innovative concepts to shape the youth to combat challenges and propagate prosperity through technology to create globally recognized professionals in the field of electrical and electronics engineering. The Department of Electrical and Electronics Engineering was started in 1998. The department was permanently affiliated to Anna University in 2008, also accredited by NAC in 2015 and accredited by NBA and has got autonomous status from 2019. The department is equipped with modernized laboratories like Electrical Machines Lab, Electronics and Circuits Lab, Simulation Lab, Control and Instrumentation Lab, and Renewable Energy Systems Lab. Our faculty and students receive grants from various state and union government organizations like All India Council for Technical Education, Tamil Nadu State Council for Science and Technology, Council of Scientific and Industrial Research, Indian Society for Technical Education, Department of Science and Technology, and Anna University. Our faculty have received a fund of 11,46,000 rupees in the past 5 academic years. Our faculty and students also published their research work in reputed international journals and conferences. Our students have received fund from TNSEST for doing projects under Student Project Scheme for 3 consecutive years. Our student has bagged a runner-up in International Quiz Contest organized by CAT Center with 50,000 cash award. Then a Chief Minister Excellence Award for E-Governance. They also won first place in Social Innovation Challenge organized by VIT University. Our student has bagged the E&SA NLC Award, Dr. Abdul Kalam Award for 4 consecutive years for showcasing their talents in technical education. Department faculty have authored books titled Research Methodology, Power Plant Engineering, Human Rights, Measurement and Instrumentation, Solid State Drives, etc. And also received copyright for Electrical Machines 1 lab manual and owned 2 patents in the title Deaf Hearing Machine for Noise-Induced Hearing Loss and an IoT model for air pollution quality monitoring system using cloud management. The Department of EEE achieved a placement record of 82.3% in the academic year 2021.
The greatest gift you can give someone is your time, because you are giving a portion of your life that you will never get back. Now I invite Professor N. Velamal, Assistant Professor from EEE Department, to introduce our resource person, Dr. C. Naveen Kumar, Senior Scientist, to the gathering.
I am delighted to take an opportunity to introduce our chief guest, Dr. C. Naveen Kumar, Technical Executive in Consolidated Metal Finishing Private Limited, and Quick Hire Scientist in CSIR, Central Electrochemical Research Institute. He pursued his PhD in Chemistry at Missouri University of Science and Technology and BTech in Chemical and Electrochemical Engineering at Central Electrochemical Research Institute. His area of expertise in electrometallurgy, or recovery of metals from primary and secondary resources through electrohydro and pyrometallurgical routes, electrodeposition of electrolytic grade manganese dioxide, graphite beneficiation from low-grade graphite ores, synthesis of boron and silicon carbide through carbothermal and pyrometallurgical routes, development of large-scale magnesium recovery from primary and secondary sources through molten salt electrolysis and electrocatalysis, synthesis of reusable, durable metal and alloy-based electrolysis for electrochemical reduction of carbon dioxide to industrially relevant value-added bulk chemicals such as adipic, oxalic, and succinic acids. Preparation of three-dimensional aerogel-based electrolytic for energy conservation reactions such as oxidation evaluation, reduction and hydrogen evaluation reactions. His ongoing research projects on one-part synthesis of multifunctional graphene metal, metal oxide aerogels, and intelligent and eco-friendly pre-paint coatings. He received CSIR Young Scientist Award in Chemical Sciences for the year 2018. We are proud to have such an eminent person for this session. We are very much happy to have you, sir. And over to you, sir.
Thank you, ma'am. Now I request our chief guest to take over the session. I request the participants kindly mute your mic during the session. If any queries, you can ask at the end of the session. And we placed a feedback link after every session. Kindly give your valuable feedbacks. Sir?
Yeah. Thank you, madam, for the nice introduction. Respected Vice Principal, respected Principal, the conveners and the HOD of the Electrical Engineering Department of IFETCE College of Engineering. So I'm Naveen Kumar Chandrasekharan. I'm working as a senior scientist in CSIR, Central Electrochemical Research Institute, Karaikudi. It gives me pleasure. It gives me immense pleasure to be here in the national level symposium today workshop on the key opportunities and challenges in recovery of metals from the lithium-ion batteries. So it's such a relevant topic, and as the Vice Principal rightly pointed out, it's a relevant topic for the current scenario because lithium-ion batteries has been extensively used. First of all, am I audible to everyone?
Yes, sir.
Yes, sir.
Okay, thank you. As rightly pointed out by the Vice Principal, this current topic, this particular topic is very, relevant and essential to be understood by the younger generations. And so I hope, the platform has been set for the students of the IFETCE College of Engineering and Technology. So just to give a brief introduction of what CSIR does, CSIR is the abbreviation, or the expansion is Council of Scientific and Industrial Research. In India, it was established in 1942. It is an autonomous society with the Prime Minister of India as its president. It's an ensemble of 37 state-of-art institutes and 3 distinct units. CSIR is amongst the foremost scientific and industrial research organizations in the world. CSIR's expertise and experience are embodied in its 4,600, approximately 5,000 scientists we work here, and 8,000 scientific and technical support personnel, and 8,000 research students work here, and we get benefited by the CSIR umbrella. Having sophisticated infrastructure and scientific and technical manpower, CSIR covers practically the entire spectrum of scientific and industrial R&D of national and international importance. So as actually CSIR works on different types of science and technologies. For example, we focus on chemical sciences, biological sciences, engineering sciences, and oceanography. And there are 37 units spread across the nation. And in Tamil Nadu itself, there are 3 units. CSIR is in Karaikudi, and SCRC, Structural Engineering Research Lab, is in Chennai, and Central Leather Research Institute is in Adyar, Chennai. So we work on a range of science and technologies, ranging from aerospace to ocean exploration, microelectronics to structural and environmental engineering, smart affordable materials to mechatronics, petrochemicals to synthetic biology, and from robotics and micro machines to drugs, pharmaceuticals, and energy technology. So CSIR, coming to the role of CSIR CSIR, it's been recognized as a energy institute where we focus on developing futuristic energy materials. Battery devices, energy conservation and energy conversion, energy storage and conversion devices. For example, batteries, supercapacitors, fuel cells, so on. We work on different diverse fields of energy. Not only that, we focus on certain areas where it is so relevant to industries, and we nurture the young minds by giving them problems on various fundamental problems on corrosion, corrosion sensors, electrochemical sensors. In hydrometallurgy or electrohydrometallurgy or pyrometallurgy. So we basically focus on using electrons as the reagent. Okay, to drive a chemical reaction, you need a chemical reagent, right? So like an oxidizing agent or a reducing agent, we need a chemical reagent to drive the chemical reaction. So hence it's called as a chemical reaction. But in electrochemistry, we use electrons. Electrons is the flow of electrons. As you guys are electrical engineers, flow of electrons is nothing but electricity. We use electricity, or in turn, the green electrons as the source for driving the chemical reactions. Hence, it's called as electrochemistry. And this institute, where I belong to, focuses mainly on the electrochemistry part of driving the chemical reactions. Okay, with this brief introduction, first of all, I would like to thank for giving me an opportunity for both the CSIR, SICRI management and the IFETCE Engineering Technology Management for giving me an opportunity to be here to present my thoughts on how this recycling is important in the current scenario of the lithium battery technology oriented devices. So with this brief introduction, I would like to present a few slides. I hope it won't bore you. So I will present a few slides, and as Madam said, you can ask questions at the end of the session. Okay.
Sir, please unmute yourself, sir.
Is my slides visible?
Yes, sir. Yes.
Okay. Thank you. So as I said before, I will be focusing on the title, Refurbishing and Recycling of Lithium-ion Batteries, a Circular Economy Insight. So I'm Naveen Kumar. I work as a senior scientist in CSIR1 Karakuri. So just a brief introduction of on Central Electrochemical Research Institute. The institute is positioned in Karaikudi, and we have 3 subunits in Mandapam, Tuticorin, and Chennai. Okay, so we are the constituent lab of Council of Scientific and Industrial Research. So we have 3 subunits. And we have around approximately 430 employees with 120 scientists, and we have 15 divisions focusing on diverse aspects of electrochemistry. And the foundation stone was laid in 1948 by our then Prime Minister Shri Pandit Jawaharlal Nehru, and it was declared open by our first president in 1953. So we also offer a course in Bachelor of Technology in Chemical and Electrochemical Engineering, where I did my BTech, and our director is Professor Dr. N. Kalai Selvi. So the research focus is primarily, we focus on batteries and power sources. As I said before, we strategize, we lay strategies to develop futuristic energy storage and conversion devices. So when I say futuristic devices, and the process, fuel cells, the sodium-ion batteries, beyond lithium, we think beyond lithium, and also we focus on developing lithium-ion batteries. And on supercapacitors too. Okay, supercapacitors is a material for storing the energy, right? So we also have another division called electroplating and metal finishing. Electroplating needs no introduction. It is being widely used in corrosion protection for decorative applications, for aesthetic applications. Electroplating is utilized and employed in various automobile industries. For example, zinc, nickel, and electroplating are done on diverse substrates to basically protect it from the damage or deterioration of their materials by corrosion, right? So I belong to the division electrometallurgy, where I focus on recovery of metal values and carbon values from primary and secondary sources, and we focus mainly on the secondary sources of the secondary sources to extract the metal values from the secondary sources. There is another division called electro-organic and inorganic, where they primarily focus on developing strategies to develop materials, futuristic materials for hydrogen generation. As you guys know, hydrogen is going to be the future energy, green energy, and there are, hydrogen is divided by different colors. So it could be gray hydrogen, blue hydrogen, and green hydrogen. When I say green hydrogen, when you produce hydrogen, it do not emit any greenhouse gases. I hope you guys know what are greenhouse gases, greenhouse gases are the gases which contribute for the global warming, and mainly carbon dioxide is the main culprit of this greenhouse, global warming, as you guys know. And coming to the, as I said before, there is another division, we focus on corrosion and materials correction, where we study the corrosion of materials in the atomic scale. And there is another division which focuses on development of electrocatalysis, catalyst for many energy conversion and storage reactions and sensors. And we also develop electrochemical sensors. So coming to the lithium-ion batteries, as I said before, electric vehicles are touted as the next big attraction in sustainable transport. In addition to the e-waste, created by end-of-life portable electronics, the increase in spent batteries generated by electric vehicles will be huge as the technology becomes widely adopted. So right now, lithium-ion batteries, as you guys know, by 2030, we will be mostly using the electric vehicles operated by these lithium-ion batteries. So the lithium-ion batteries, batteries is a galvanic cell. I hope you guys know about it. Battery, it is nothing but an energy storage device where we convert the chemical energy to electrical energy. Hence, it is called as galvanic cell. An electrochemical cell can be divided into two types. One is the electrolytic cell and the galvanic cell. Electrolytic cell is nothing but cells which is being used for electroplating, where you give energy, electrical energy, and this electrical energy is converted to chemical energy. But in the case of galvanic cell, your chemical energy is converted to electrical energy and it is stored. Okay, so it is called as battery. Okay, so batteries can be divided into primary and secondary cells. Primary cells cannot be recharged. What we use in the household batteries, the manganese-based batteries. You can't recharge those batteries, but in the case of lithium-ion batteries, it could be recharged. And the primary chemistry behind this lithium-ion battery, if you take any electrochemical cell, it will consist of an anode, cathode, and an electrolyte. The anode, in the case of, if you take an electrolytic cell, in the case of anode, the oxidation takes place. In the case of cathode, the reduction takes place, and the electrical conductivity takes place between these two electrodes, and the ionic conductivity takes place in the electrolyte. But in the case of the battery, the anode is here in lithium-ion battery. We use graphite as the anode, and due to its inertness, and we use cathode. We have cathode where the transition metal oxides. Okay, transition metal oxides. For example, there are different types of cathode materials are used. For example, lithium cobalt oxide, lithium manganese oxide, lithium nickel cobalt oxide, lithium NMC. The NMC is nothing but nickel manganese cobalt oxide in equal proportions. And right now we focus on lithium iron phosphate materials, because as Madam rightly pointed out, lithium ion batteries can succumb to easily. It can get ignited. So we use a material called phosphate, which do not initiate or propagate the ignition. So preventing it from explosion, right? So In the case of the lithium-ion batteries, the charging and decharging occurs by the intercalation of lithium ions into the carbon lattice, where this lithium is intercalated between the carbon, and then it gets deintercalated. That is the discharge process. Okay, so in the case of batteries, we don't go for oxidation or reduction, but we say charging and discharging. Okay, so there are three different types of basic cell designs. One is cylindrical, prismatic, and pouch type cells. So the salient features of the rechargeable batteries or the lithium-ion batteries is it can be recharged. It has high energy density. It has high power and long life. Okay, but one of the disadvantages is it could easily get ignited. But the problem is being addressed right now, and the cathode materials which do not propagate the flame, or the which arrests the ignition, is being researched at our lab and worldwide. So the applications of these lithium-ion batteries, as you guys know, we use mobiles, and everyone has mobiles these days, and everyone has laptops. So we use lithium-ion batteries in day-to-day life. And now industrially automatic vehicles, and you can see electric vehicles these days. Even in Karaikudi, I could see the electric vehicles or the scooters coming up charged with these lithium-ion batteries. So what are the bottlenecks of these lithium-ion batteries? Of course, lithium-ion batteries, as I said, is one of the most popular forms of energy storage in the world. And by 2019, 3 scientists were awarded Nobel Prize. Dr. John B. Goodenough, Dr. Stanley Whittingham, and Dr. Akira Yoshino. They were recognized for research laid to the foundation of this particular lithium-ion batteries, which is being widely used by the humankind, I could say, across the nation. Okay, so as I said before, the lithium-ion batteries consist of lithium metal oxides in the positive electrode, where lithium ions can be stored, and carbon in the negative electrode. The electrolyte, as I said, between the anode and cathode, the electronic conductivity or the flow of electrons takes place. But in the electrolyte, here we use organic electrolytes because, as you guys know, lithium, it could easily react with the moisture. So moisture, we should not have any moisture in the lithium-ion battery package. So we should not. There should be ppm level of oxygen or moisture should be present in. There should be no moisture even in the ppm level in the electrolyte. So what is the primary lithium electrolyte which is being used here? It is nothing but organic carbonate. We call it as propylene carbonate. So it is the organic electrolyte which is being used. And this particular electrolyte, it transfers the ions. It assists the ionic conductivity between the anode and between the anode and the cathode, or the vice versa, cathode and the anode. During charging, lithium-ion passes from the positive to we call it as positive, and the negative electrodes, positive to the negative electrode, while the opposite occurs during the discharging. Lithium batteries do not require temperature monitoring to ensure effective operation. The large demand for lithium-ion batteries is due to their accessibility and reliability, and many technologies, as I said before, electric vehicles, hybrid electric vehicles, they rely on these lithium-ion batteries due to their high energy density. The advantage of lithium-ion batteries may lead to the use in production of large-scale storage system, even if storages will be expensive. So why do we have to go for the lithium-ion batteries? Because of the straightforward reason of using the fossil fuel-based energy. Right now you guys know what is the price of petrol or diesel, which is being extracted from the crude oil, which is being primarily imported from the other countries. For example, we focused on the Gulf countries, right? So the prospect to transform, and also when we use this fossil fuel based energy, it could be coal, it could be oil, where we burn and we emit a lot of carbon dioxide, and this carbon dioxide is the main reason or culprit for the global warming, which has a direct implication in raise of the temperature of the Earth, right? So what does it? To be precise, CO2, it becomes. It goes and kills your stratosphere, and there is holes are being found in the ozone and the ultraviolet rays. It affects us, and it also leads to other health complications to us. Okay, so to avoid this carbon dioxide, and provided if your lithium-ion batteries are recharged by renewable sources, for example, solar, wind. Wind is the most environmentally benign form of extracting energy. Because it leaves no carbon footprint. Pretty much closer to nil carbon footprint. So if you could use wind-based energy, definitely this lithium-ion batteries is going to have a direct is going to have a benign benefits to our ecosystem. Okay, so the prospect to transform the transportation sector, domestic and industrial, which currently contributes major amounts of carbon to the atmosphere. It provides a solution to the intermittent energy produced by solar and wind generation, as I told you, aiding to make these green energy alternates more practical and viable. Nevertheless, batteries may not be cleaner option, as I told you. Batteries may not be cleaner option until we employ energies extracted from the wind or solar energy, which is the renewable energy sources, right? So again, we use, as Madam rightly pointed out, in the case of lead acid batteries, it is just lead, okay? Only lead. So it could be easily melted, or by some hydrometallurgical techniques or pyrometallurgical techniques, and you just have sulfuric acid. So it could be either converted to metal or in any of its form, lead oxide or lead sulfate, and it could be purely extracted. But as I said before, in the first slide, where they use a lot of components in the lithium-ion batteries, where at the cathode they use different transition metal oxides, a mix of transition metal oxides and lithium, and in the case of anode they use graphite, and electrolyte we use organic electrolyte, which is propylene carbonate, right? And we have we use current collectors like aluminum, copper, etc. So if you have to build a lithium-ion battery, there are a lot of multi-component systems which is being involved in getting this lithium-ion batteries to a shape, okay, to the useful shape. Sourcing these materials. So what do we have lithium in our nation? No. Okay, and when it comes to nickel and cobalt, of course, we don't have any much resources to extract this metal values.
Sir, excuse me, sir.
Yeah.
Sir, your slide is not changing, sir. We are still in the title slide.
Oh, is it? Oh, sorry.
Yes, sir.
Now is it? Now is it changing?
No, sir. You can go for the full screen mode, sir. Slideshow. Now it's changing, sir.
Is it changing now?
Yes, sir.
Now I am in lithium ion batteries global and Indian market. Is it changing?
Lithium ion batteries. Yes, sir. It's
lithium ion battery, LIB global and Indian market. Is it?
Lithium ion batteries versus fossil fuel based energy.
Oh. Now I am in the next slide, LIB global and Indian market. Is it changing now?
Sir, you have to go to the slideshow, sir. Slideshow.
It is in slideshow only.
Full screen mode, sir.
Okay, I will share it again. Now?
Yes, sir.
Is it changing now? Yeah.
Yes, sir. It's changing, sir.
Okay. So sourcing these materials, sorry for the interruption, and sourcing these materials, mainly the metal values, lithium and transition metal derivatives. Carbon, we have good amount of good source. So we need not worry about carbon, but what about the other elements? I mean, cathode elements. I mean, we don't have any source in our nation, so we need to look for a methodology to readily to have ready access to this particular metal derivatives, right? So amidst these concerns, experts predict that lithium-ion batteries will play a significant role in global cleanup of its energy sector through refurbishing and recycling of metal values in lithium-ion batteries. So like we have awareness, I mean, at least in our nation, we have awareness of recycling many many things such as plastics, which is being used widely by every one of us. But we have to reuse it because if we burn it, we get it may lead to harmful harmful effluence, which will affect our health. So same basic principle applies over here for lithium-ion batteries. If we discharge, if we discard it in an improper way, in an informal way, it may, I mean, the metal values which is in the which is present in the lithium-ion batteries, it may contaminate the soil, groundwater, etc., leading to harm, leading to health issues to the human. Okay, so hence the refurbishing and recycling of the metal values is imperative here. So I have gone to the second slide. Is it changing now? The LIB global and Indian market.
Yes, sir. Yes, sir.
Okay. Thank you. So the global global lithium-ion battery market is expected to increase. Okay, is expected to increase, as you could see, from 2019 to 2027. I mean, everyone pretty much right now everyone is using lithium-ion battery in the form of mobiles and laptops, and everyone, in the household, everyone has mobiles and everybody uses laptops these days. So there is no escape of lithium-ion batteries. Internationally. So it says the dependence of humankind in this particular lithium-ion battery market. And of course, as you guys know, the lithium-ion battery is imported from various countries such as China, Korea, etc. So there is a need for import substitution in this lithium-ion batteries. And provided in the negative side, we don't have any resources of this lithium metal values. So that's why we are looking into how to recycle the the metal values which is available with us. Okay, so once we in a very efficient way and in a very formal way. Okay, so the market for lithium-ion battery in India is expected to register a compound annual growth rate of 17.2% between 2020 and 2027, and the market value of lithium-ion batteries in 2020 is USD 1.66 billion, which is huge, and the estimated market value is going to be in 3 times more in 2026. Okay, so the market, there is no going to be any decline in the global and Indian market of lithium-ion batteries. Okay, I'm moving to the next slide. Okay. So what do we have? As I told before, a lot of applications are there for lithium-ion batteries, and currently it is being used commercially in various applications. Say like mobile, smartphones, electric vehicles, etc. So how do we discharge it? As I said before, it has to be recharged by renewable sources, and also the landfills. Which may occur due to the when we discharge it, it may lead to other health complications to us. Okay, so as I said before, there are different components present in the lithium-ion batteries. For example, aluminum. So we have almost $1,250 per. These are the economic values of components in lithium-ion batteries. Where in the cathode alone, we have aluminum, lithium, cobalt, nickel, and manganese. Okay, we don't have any issues with aluminum and manganese. The resources are available, but what about lithium, cobalt, and nickel? Okay, lithium, it is widely present in. It is being imported from Australia and Chile, and cobalt from Congo, and nickel also from African countries. So we need these resources to be tapped, and the only way to extract these metals is by recycling. Okay, so coming to the concentrating on the cathode composition, we can say a lot of cathode compositions has been arrived, as I told you before. Right now in our mobile devices, in our mobiles and the laptops, we use lithium cobalt oxide, where only lithium and cobalt is alone present. Okay. So before that, before getting into the detail, and of course, I mean, being an electrical engineers, you may be aware of electromotive force series. So why do we use lithium? Because it has the highest potential. It is very reactive. So that's why we use lithium. Its standard electrode potential is negative 3.05 volts. So when you combine these lithium and carbon, it gives around 3 volts. Okay, so that's why we go for this lithium. Okay, so why lithium? This is the reason. Okay, as I said before, we use lithium cobalt oxide, NMC. NMC is nothing but nickel, manganese, and cobalt. NCA is nothing but nickel, cobalt, and aluminum. LFP, as I told you before, to arrest this ignition. I mean, to these explosions, right? So they use phosphate-based compounds. I mean, phosphate-based compounds are well known for arresting these sparks. I mean, ignitions. I mean, it do not propagate or the sparks, right? So preventing them from explosion. So that's why we use lithium iron phosphate. Iron is okay. I mean, we have a lot of steel industries to supply us iron, but what about lithium? And in the case of lithium manganese oxide, as you said, MOIL, I mean, Manganese Oxide India Limited, they can provide us manganese oxide, but what is the source? How are we going to source the lithium ions, right? So these are the structures. Just to give a brief introduction of the cathode materials. Okay, cathode materials, LCO, as I told, LiCO2. The chemical formula of LCO is LiCO2, where you could see, I mean, only lithium and cobalt metal values are present. In LFP, only lithium and iron metal values. In LMO, lithium and manganese values. In case of NCA, lithium, nickel, cobalt, aluminum, and in case of NMC, we have nickel, manganese, cobalt, and these are the structures. Okay, mostly this layer structures, except for your LiMn2O4 is a spinel structure, and LiFePO4 is as the olivine structure. So there are many uses of these cathode materials. As I said, LFP is mainly used to prevent is prepared keeping in mind the safety of the product. I'm going to the next slide. So coming to the lithium resources, so what are the global and national lithium resources in the case of extracting this lithium, right? So lithium is mainly present on the sea brines, right, on the rocks. Okay, so what are the types of lithium ores? It's petalite. Petalite is nothing but lithium and aluminum silicate. Lepidolite, which contains a lot of minerals, where selectively we have to remove the lithium. And spodumene, which is lithium aluminum silicate again, but in a different form. Okay, so as I said before, Chile has the world's largest known lithium resource, followed by Australia, Argentina, and China. So do we have lithium sources in India? Yes, we have, but in a very least concentration. In Karnataka, Andhra Pradesh, Andhra Pradesh, and Gujarat. Okay, mainly in the valleys. Okay, so and also the lithium brine is present in the Samba and Pachpatara playas. So coming to we don't need as lithium metals, because lithium metal is very dangerous to lithium metal is very dangerous to lithium metal is very dangerous to maybe sorry about that. So lithium ion batteries, lithium metal values, or lithium metal can be extracted only by the molten salt electrolysis, and we don't need any lithium metal over here because we are concentrating on lithium ion. So we can go for the salt version of the lithium carbonate. So the current market price of the lithium carbonate is $20,000 per ton, and the current consumption is 68,000 tons, and the expected demand is going to be somewhere in lakhs. By 2050, it's going to be 4 crore tons. Okay, so the consumption is going to be pretty high in the case of lithium carbonate. So we need to source this lithium carbonate, either from the primary source, or either we have to import it, or we have to recover from the lithium ion batteries which has been already used by the consumers, right? So lithium production, how do they make lithium? How do they make this lithium carbonate? The conventional method of making lithium carbonate is by brine. Okay, brine is nothing but seawater, where the seawater consists of a lot of minerals. For example, magnesium, sodium, and as you guys know, that if you go to the coastal side, you can see. We extract salt from, sodium chloride from the seawater. So exactly pretty much the same process, but at different density, they extract. Lithium ions, right? Lithium ions in the form of lithium carbonate selectively by various processes, and precipitation is one of the process. And also we have other membrane processes to selectively separate lithium ions based on their size. Okay, based on the lithium ion size, we can selectively remove the lithium ions to lithium carbonate, right? So what about cobalt and nickel reserves across the globe? As I said, India has no sources of these metals, and these metals are very important to maintain the structural stability of these lithium cathode materials, and the cycle life is also very important. As you guys know, in any kind of a battery, your cycle life is very important, and the rechargeable batteries does that job. So that's why we focus on these lithium ion batteries. Okay. So the cobalt and nickel are extracted through hydrometallurgical process. What do you mean by hydrometallurgy? Metallurgy is nothing but extraction of metals, and hydro is nothing but water. So we use water-based metallurgy to extract these metal values. Okay, so that's why it is called as hydrometallurgy, followed by reductive smelting. Smelting is nothing but what we do in the case of iron. In the case of iron, we start with iron oxide. We react it with carbon at higher temperatures using blast furnace. We end up getting iron and a little amount of carbon, but a lot of carbon dioxide is being emitted in this reductive smelting. But in the case of, on the other hand, if you go into these transition metals, right? So, for example, cobalt, nickel, and copper. Copper, as you guys know, the famous sterlite copper, they does the job of converting this copper sulfate to copper metal for various applications. Mainly focus on the electrically conductive applications. Okay, so we can use that electrolytic process for converting this cobalt, nickel, and copper to copper sulfates or salts to their respective metals. Okay, metal values. Okay, the cobalt reserves in metric tons. As you could see, Congo leads the chart, followed by Australia, Cuba, Philippines, Russia, Canada, Madagascar, China, US, South Africa, and Morocco. Right, in the case of cobalt reserves. And in the case of nickel reserves, Indonesia, and again Australia, Brazil, Russia, Cuba, and Philippines. They have the most major cobalt and nickel reserves for this purpose, for building a lithium-ion battery. Right? Okay. So as I said before, and I have reiterated many times. Why we need the lithium-ion batteries to be recycled due to the scarcity of the metals or the paucity of the metals, environmental hazards. As I said, if you discard these lithium-ion batteries in an improper manner, then definitely it will lead to contamination or polluting your soil, and thereby polluting the groundwater, and it will lead to definitely health hazards. And finally, as I said, if the source of electricity for charging or using your lithium-ion battery is green, if it is renewable energy source, definitely it will help you in reducing the greenhouse gas emission. Okay. So we have created a lot of lithium-ion battery waste has been created. See, in 2012, this is globally. In 2012, it was only 10,700 tons. But in the case of 2020, it went up to 250,000 tons, and by 2025, it is like 464,000 tons, which is huge, right? So which is huge, and we have to regenerate or reclaim it some way so that it will be used as a value-added product. It could be either it could be either used in the lithium-ion battery, recreating the lithium-ion batteries, or for some other purposes. So the key suppliers, our favorite China, South Korea, and Taiwan, they are the key suppliers. As you know, the political background behind between India and China, and anytime they can supply, they can stop the supply. So India relies mainly on these countries to import. So we are in a position to either for import substitution, where we can recycle these metal values from the spent lithium-ion batteries, right? So how lithium-ion batteries is used in electric vehicles. Some of the what are the other short-term solution other than this recycling? Some of the potential second life uses for lithium-ion batteries. So if you use it, but it cannot be used for for main applications. But what are the other applications? So say for example, electric power management for residential and commercial spaces. Power grid stabilization, and the renewable energy system firming by providing storage, and these car manufacturers has already made some plot, for the second life initiatives by the automobile companies for these applications. So these are these. So this slide focuses on how without recycling these these lithium-ion batteries could be used for other secondary applications, not for the primary applications, but for the secondary applications. So getting into the deal of how to recycle this lithium-ion batteries. So the spent batteries, first it has to be sorted out. It has to be sorted out whether it is a rechargeable battery or a primary battery, or what kind of batteries for the applications we use. For example, it could be mobile batteries, it could be laptop batteries, or it could be electric vehicle batteries. It has to be sorted out. It has to be discharged. It is very important because if it is charged, then it may lead to explosion. So it has to be discharged. It has to be disassembled. So we remove it. So there are disassemblers and shredders which is available in the market, which does the job. But right now in our lab, we do it manually, and we pre-treat it, right? So either thermally, physically, chemically, mechanically, or mechanochemical. So we pre-treat it to remove the electrolyte. So electrolyte, as I said, is an organic electrolyte, so we have to remove that by using a solvent, and we remove this anode and cathode cathode, which is being applied, which is already applied on the current collector. So the current collector, major current collector which is being used, main current collector which is being used is copper. So copper will be as metal sheets. So that can be recovered, and the cathode and the anode values, it could contain some lithium ions and graphite. But in the case of cathode, it will contain the main metal values, for example, transition metal values and lithium ion values, right? So what are the processing methods to remove these metal and carbon values is hydrometallurgical. As I said, hydro is water, metallurgical is extraction of metals. This particular method is being done, practiced at a very low temperature. So maybe the maximum temperature we could reach over here is approximately 100 degrees C. But in the case of pyro, right? In the case of pyrometallurgical route, pyrometallurgy, as I said, one example is extraction of iron, where we go for higher temperatures, say like 900 to 1000 degrees C. And also I gave an example of extracting this lithium metal from lithium carbonate or lithium chloride, where we employ higher temperatures, say like close to 700 to 800 degrees C. So it is a pyro. Pyro is nothing but fire. Fire. So we employ fire or high temperatures to extract the metal values. And coming to the biometallurgy, we use bioenzymes or bioorganisms, microorganisms to reduce these metal values or oxidize these metal values. And the other route is to refurbish. What do you mean by refurbish? What is the difference between this recycling and refurbishment? Refurbishment is nothing but you take the, you just dismantle it. You see what is deficient in the cathode material. If it is deficient of say like if it is deficient of lithium ion, you add some lithium ions, you recook it, you employ it again for the in the same battery. Okay, so it's like add giving vitamin tablets or nutrients to your body, right? So that is called as refurbishment. Okay, so this is the primary routes for recycling of this or refurbishment of these lithium ion batteries. Okay, so this is the comparison of different recycling routes. I mean, starting from best to worst. Okay, so coming to we compare three different type of primary methods for this recycling. So one is the pyrometallurgy, the other one is hydrometallurgy, the other one is refurbishment. So as you could see, the TRL is nothing but technology readiness level is good for in the case of pyrometallurgy, and better is best for pyrometallurgy. It is better for hydrometallurgy, and it's close to worse for this refurbishing, because still the methodology has to be the methodology has to be established in the market, right? The complexity is refurbishing, and pyrometallurgy is easy, but hydrometallurgy is somewhere in between good and better, right? So purity of the required material. See, I mean, when you get in the case of pyrometallurgy, the purity is really bad, but in the case of hydrometallurgy, the purity of the required material is very good. Okay, so the end of the day, the recovery efficiency in purity is very important. Okay. So again, the quantity of the recovered material is in hydrometallurgy, it is high. Probably it is next to pyrometallurgy. In the case of refurbishing, it is the highest, it is the best, because we don't do any leaching process, or we don't do any other chemical processes for extracting these metal values. Rather, we add some metal values to the existing one, and we reuse it for the next purposes. Okay, for the next purposes. For it could be a second life purpose or the primary life purpose. So the waste generation. In the case of waste generation, pyrometallurgy, it leaves a lot of harmful gases, because if you have cathode, if you have anode, which is nothing but a carbon, when you heat it again, I mean, you emit a lot of carbon dioxide. But in the case of hydrometallurgy, it is next to pyro, and refurbishing, I mean, it is better than those these recycling methods. Okay, energy usage, as I said, I mean, we go for higher temperature. So a lot of energy is being used in the case of pyrometallurgy. In the case of hydrometallurgy, it is next good to the pyrometallurgy. So hydrometallurgy and refurbishing, they fall on the same line. Of course, the capital cost you need, I mean, as you know, in the case of hydrometallurgy, just a beaker or a reactor should be good enough, and you just heat it to a temperature up to, like, say 80 to 100, which is good enough. But even in the refurbishing, you just add what is the deficient metal value, and you just go ahead. But in the case of pyrometallurgy, we need it is higher temperature. Okay, and also it needs a specialized furnace for this particular methodology to be practiced. Okay, so the production cost, but when you see the overall, the production cost is good for pyrometallurgy. Then comes the hydrometallurgy, and comes the refurbishing, right? So based on these diverse vital factors, right? So whenever we develop a technology, of course, we have to look into the techno-economic values of that particular process. Okay, without a good economic value in meaning it, you should end up getting some profit or no profit, but not loss. I mean, you should not end up in the negative side. So we need to develop technologies. We have that constraint in developing technologies and commercializing in the market, or for a tech transfer to an industry. We have to consider these factors, which is mainly the production cost, the metal recovery efficiency, the purity, and more importantly, the energy. Okay. So for having said that, I mean, if you use the energy from say non-renewable sources, for example, fossil fuels, I mean, the whole process do not make any sense. I mean, it does not make any sense because you emit a lot of carbon dioxide in generating that electricity. So we need to focus on renewable energy source for these processes to happen in a net zero carbon emission zone. Okay, so so having considered these these factors, I mean, we go for the hydrometallurgy concept of of recycling these metal values from spent lithium-ion batteries. Am I clear so far? I mean, if you have any doubts, I can stop here. You can ask me if you have any questions. Then I will go ahead. Is it fine? Can I go ahead? Is it fine? Can I go ahead? Is everything fine?
Yes, sir. Yes, sir. Yes, sir.
Okay. So I'm on the slide LIB's waste management. Okay.
Okay, sir.
Okay. So when it comes to a car where electric vehicle, we have if you use lithium-ion batteries, so what are the recovered components from these lithium-ion batteries? We will have a look at it, and we will look into what are the challenges. What are the challenging factors which we have to face if we have to really seriously look into this LIB's waste management. Okay. So what are the recovered components, first of all? Okay, bus bars, electronics, wiring looms, modules or cells, and other components. I mean, there are multi-components which is associated with these things, right? So what are the recovered components? Casings, terminals, and cells. Okay, these are the ones which we could recover. And what are the recovered materials? As I said, the cell chemistry and recycling process. Hydrometallurgy we can use, and we can recover plastics, the metal values such as aluminum, manganese, lithium, nickel, cobalt, copper, and graphite. Okay, graphite. Okay, so what are the disassembly problems? Variety of vehicles and shapes and sizes are available. Okay, so that is because it starts from a normal car to an SUV to trucks. Okay, so we need to have there are a variety of shapes. So we need to adjust ourselves to focus on which electric vehicle will have the major components of what content. So the composition is very important, right? So different pack configurations and locations, different fixings and toolings are required, and so on. I mean, the weight of the battery, everything. I mean, starting from the cylindrical cells to pouch cells to whatever it is, and the composition of the cathode and anode materials would not be same. It would have different nanomorphologies. So these are the risk factors. I mean, challenging factors in this particular LIB's waste management. So the challenging factors is high investments in technology for collection, transportation, and management. Lack of awareness is another crucial challenge among the battery producers as well as end consumers. Only battery manufacturers can tap the market through extended producer requirement norms, because only the battery manufacturers will know what is the components which is present in the battery, and also the composition, right? The composition is very important over here. Otherwise, we have to do some analysis and we have to know, I mean, what are the metal values in the battery which is being given to the market, right? So safety issues, as I said, I mean, you have to discharge your battery. There's no other go. If not, it may lead to explosions. Okay, safety issues. So as I said before, the safety is risk related collection, transport, and storage. Collection and transportation of waste lithium-ion batteries is a difficult task because it may, as I said, it may range from small. I mean, some would not be discharged. That would lead to a safety issue. So there are a lot of challenges in transporting these waste lithium-ion batteries from one end to another end. Okay, less than 5% of the lithium-ion batteries that are being collected today. Only 5% of the lithium-ion batteries which are being spent are being collected today. So okay, so in the 100%, only 5% is collected and reused and recycled for secondary life, or again it is being rejuvenated or recouped as the rechargeable batteries for the primary users. So the awareness, we have to create awareness. We should not I mean, this could be a good platform because I could see a lot of students having. I also teach courses over here. I can see a lot of students having 2 or 3 mobile phones. So so when you, once the life of these mobiles are over, please be responsible in discarding these batteries. Also the mobile. Okay. So formal collection booths could be. I could see some collection booths in IIT when I visited last time in a couple of months before. So it could be practiced everywhere, and that could give us awareness to the public. And moreover, it could, our students could be the messages of translating the giving this important message to the public. So, who are the global players in lithium-ion batteries recycling? There are, as I said, the 2 important concepts or 2 important routes, which is the pyro and hydrometallurgy is mainly used in extracting this metal value. So, you could see some known names: Sony, Batrac, Curec, Snam, Unicor. So they are the global players. There are many companies which they focus on retrieving these metal values and the carbon values and the cell components, plastics to useful materials, and reuse it for the next. For reuse it for synthesizing or designing new lithium-ion batteries. So the prospect of lithium-ion battery recycling is high in India. As I said before, by 2030, the Indian government mandate is to have lithium-ion batteries or the EVs, electric vehicles, to be owned by us. To be owned by us. So lithium-ion batteries will play a major role in that, right? Okay. So having said that, there is a since we are going to use it, there is a lot of market potential for this particular lithium-ion batteries. And going by the battery manufacturing target set by the NITI Aayog under its energy storage vision by 2030, the cumulative lithium-ion battery recycling market is estimated to be about 160 gigawatt hour, which is huge. Okay, so the prospect is going to be is going to be high, and the benchmark is going to be high. So we have to definitely be prepared for that. Okay, so the lithium-ion batteries recycling in India is also occurring in the formal sectors, mainly focusing on the hydrometallurgical concepts, because here we don't have energy. Energy is expensive over here, so we don't opt the pyrometallurgical routes. As you could see, very good names. For example, well-known names: Tata Chemicals, Atero Recycling. They focus on Eco Tantra, and there are some informal sectors also. Mahindra Electric. And there are some informal sectors also. These are well-organized formal sectors where they take this job seriously, and they without any harmful emissions or without any harmful emissions and harmful contaminants which is being emitted after the recycling to the environment. They take it very seriously, and they do this lithium-ion batteries recycling to extract these metal values. But there are some informal sectors, and government is also taking measure to formalize these informal sectors to focus on recycling these metal values from the lithium-ion batteries, and also in e-waste, so that the effluents are not let out or let into the soil, or which contaminates the groundwater, right? So what are the regulations, government regulations, for lithium-ion batteries recycling around the world? So, if you see the Western countries, for example, European countries, there are regulations. Battery Directive 2006 is the regulation where the collective target is to collect 45% of the used lithium-ion batteries. The collection model is state-funded. Environmental agreement has been done. There are many competing organizations which is being employed, and without these organizations, some informal collection model also has been initiated by these European countries. And similar lines, China, US, and Japan they also have a collection module for collecting these lithium-ion batteries. At present, India do not have any policy framework, but it is being framed by NITI Aayog for the mechanism of lithium-ion batteries recycling and second use market. As I said before, India has already issued a proposed legislative framework for the waste management and recycling of lithium-ion and nickel-cadmium batteries, right? So what do we do in CSIR1? We do refurbishment, we do recycling, and we do smart battery management of lithium-ion batteries at CSIR1, where where we refurbish. As I said, refurbishing and recycling is different. Recycling is cutting open the batteries, we extract the metal values, we recook again, and we make the new lithium-ion batteries. But in the case of refurbished lithium-ion batteries, as you could see, we could imitate, by just putting in, it's like dosing the vitamin tablets into your body or protein into your body to make you rejuvenated. Exactly the same thing. What we analyze what is deficient at the cathode, and we add the metal values into it in the form of the salts, and we could get pretty much the same results of what the new lithium-ion battery does, right? And we also, one of our scientists, she's also working on smart battery management of this lithium-ion batteries through some simulations, right? So as I said before, so this is where I concentrate on, where we recover the metal values from the cathode material of spent lithium-ion batteries. So first we get the spent lithium-ion batteries, we crush it, we take the active material, we leach it with an acid. Then in the leach, and we get it contains a lot of mixed metal ions, which is being selectively precipitated towards respective lithium salt and the transition metal salts. So what you could see here is the cobalt in the form of oxalate, lithium in the form of carbonate, and NMC. NMC is nothing but nickel, manganese, and cobalt as a precipitate in a solution, as in the form of a solution, where we achieve the leaching efficiency. Leaching is nothing but dissolving the metal ions which is present in the cathode into the solution by using acid. Okay, so that is acid. It could be an acid or an alkali, right? So leaching efficiency we have achieved greater than 95%, and product recovery is nothing but how much it is in there. It is there in the cathode material, and how much you have got after the process. Okay, so it is between 85 to 95%, and it may vary accordingly, according to the composition of the material. So as I said before, the techno-economics plays a huge role in doing anything, right? So without economics, we can't do anything. So we also checked the price of the required material and the commercial material, which has a significant difference. Which has a significant difference in the economic values. So that's why we proceeded with this particular technology. Okay. So in summary, the three methods, the recycling and refurbishing, and in recycling, the ionometallurgical method, pyrometallurgical method, and refurbishing plays a very huge role in recovering these metal values. And considering the depletion of the conventional fossil fuels and emission of greenhouse gases, as urged to look upon alternate energy storage and conversion technologies. So that's why we went into lithium-ion batteries. Rechargeable lithium-ion batteries are considered promising energy storage devices due to their high energy density, power, and long life. Okay, and of course it's rechargeable. The inevitable increase of electronic gadgets and EVs, which employs lithium-ion batteries as the energy storage device, is escorted by sporadic use of various raw materials. Okay. So, as I said before, there is a lot of raw materials are being used, okay, starting from lithium to cobalt, nickel, manganese, copper, aluminum, etc. So, it is very important to source or supply chain of this of these raw materials are very important in designing or developing the lithium-ion batteries in our country. Okay. Owing to the limited lithium and transition metal resources available across the globe, it is imperative to address the spent battery accumulation through smart management of refurbishing and recycling via safe, economical, and eco-friendly chemical and metallurgical methods. Okay, so that is very important. It has to be safe, it has to be economical, and it has to be eco-friendly. Okay, so again, I mean, when you're recycling something, you should not leave any harmful influence to the environment. I mean, it could be soil, it could be it should not be let into the air, it should not be let into the soil, or it should not be let into the water. Okay. So we have a lot of past tragedies because of in India, because of letting out these effluents. I mean, in an informal way, without any knowledge of what we are letting out, right? So considering the production and energy costs, direct refurbishing and hydrometallurgical methods could be adopted for effective recycling of the metals and other valuable materials from the spent batteries. So these, I mean, refurbishing and hydrometallurgical methods in particular in the recycling could help us in effectively recycling of in effective recycle of these materials from the spent batteries, particularly from the cathode and the anode materials. So with this, I would like to thank everyone for your kind attention. I would like to give a special thanks for inviting me for this particular session. I mean, which is most relevant to me, and your valuable feedback is would help me to move forward. And I would like to give a special thanks to the management of IFETCE College of Engineering, and of course to my mentor, Director CSIR1, and my past and previous HODs. And of course, without students, nothing can happen. I mean, they support me a lot in my R&D activities of this recycling of these metal values. Thank you. If you have any doubts, you can ask me.
Yes, thank you, sir.
Yeah.
Thank you so much, sir. Participants, you can unmute now your microphone and you can ask your doubt.
Sir, is it have any best battery than lithium ion, sir?
Best battery than lithium ion? People are designing. I mean, this is the commercially successful battery is lithium ion, and people right now they are focusing on sodium ion batteries. Okay.
Okay, sir.
Sodium ion batteries. Because sodium is available in plenty, so people are focusing on sodium ion batteries. But right now, lithium ion batteries, I mean, it's at the top.
Okay, sir. Thank you, sir.
Dear participants, you can ask your queries, or else you can post your queries in chat box.
I mean, if you guys have any queries, you can also email me, or you can contact me through the convener, Mr. Jay Shiva sir. I mean, I'd be happy to help you guys.
Thank you, sir, for giving your valuable concepts on recycling electric vehicle batteries. And I'm sure that your address will help you a lot in understanding the basic ideas on electric vehicle batteries. Thank you, sir.
Thank you, madam. Thank you. Thanks a lot. Thanks a lot.
Dear participants, feedback link has been posted in chat box. You can fill the feedback form. Let's have a lunch break now, and we will resume sharply by 2 p.m. Thank you.
Thank you all. Thank you all.